Welcome to A and As Level Physics lecture series. Today, I will teach you chapter number 9. The title of chapter is Current Electricity. And this is the course outline of this chapter. First, we will cover electric current, then potential difference, power, and in the third part of the chapter we will discuss resistance and resistivity, and in the last part of the video, we will solve some of past paper questions for practice. And if we talk about electric current, then electric current is basically the flow of charge carriers. And if we talk about the charge carriers, then in an electrolyte solution charge carriers are positive and negative ions, and in a metal wire, the charge carriers are free electrons. Actually, in metals, atoms are fixed, so only free electrons can move. Applying a potential difference causes electrons to move with a drift speed, creating electric current. The unit of electric current is ampere, defined as one coulomb of charge passing through a cross-sectional area in 1 second. To measure current, we use an ammeter and it always connected in series. In this diagram, a battery is connected to a resistor. And the current passing through this resistor is 0.09 amperes. The device used to detect the current is called a galvanometer. It is very sensitive, which is why only a small current is sufficient for full-scale deflection. To enhance its range, a shunt resistance is connected in parallel. Usually, the value of this resistance is very small compared to the internal resistance of the galvanometer, so a large current passes through this resistor while only a small portion of the current passes through the galvanometer to avoid full-scale deflection. The range of the galvanometer is decided by the shunt resistance. A multi-range ammeter can be developed by using a selectable switch as shown in the circuit diagram.
The design formula for the shunt resistance is given by, where Rs is the shunt resistance, Ig is the full-scale deflection current of the galvanometer, Rg is the internal resistance of the galvanometer, and I is the total current to be measured.
Numerical problems will be solved in the last part of the video. The charge on charge is quantized. This is our next topic. To understand this topic, consider these two diagrams. The first shows discrete steps while the second one consists of an inclined plane. In the first diagram, if we consider the height of the step to be 10 cm, then you have the discrete steps multiples of 10 cm. You can step up at 20 cm, 30 cm, 40 cm and so on. You can't step up at 15 cm. But in the second diagram the height is continuous, you can reach up to any height. In the same way, charge also occurs in steps, not continuously. For example, the charge transferred between bodies is in multiples of the charge of one electron, which is approximately minus 1.6 x 10 raised power minus 19 coulombs. Now, let's solve a small question. How many electrons constitute one coulomb of charge? Using the formula Q is equal to Ne, where Q is one coulomb and E is the charge of one electron, we find the answer, approximately 6.25 x 10 raised power 18 electrons. Consider another relationship of electric current. Electric current equals to ANVQ, where A is the cross-sectional area, N is the number density of charge carriers, V is the average drift speed of free electrons, and Q is the charge on an electron. This relationship is very important and extensively used numerical. Let's derive this expression. For this, consider a metallic conductor attached to a battery with length L and cross-sectional area A. Using the relationship I is equal Q by T, where Q is charge and T is time. To find the total charge inside the conductor, consider its volume and the number of electrons. Now multiply it by Q to get the total quantity of charge which is free to move. Now, what would be the time taken by the electron to travel through the cross-section? Use the formula for speed, and it would be L by V. Now, we have the expression for both, total amount of charge and total time taken. Substitute these values in the formula for current. Rearrange to get the formula. So this is the formula, which we want to derive. Now, let's discuss two commonly used terminologies, drift speed and current density. When talking about drift speed, consider the movement of free electrons in metals. In metals, free electrons move like gas molecules. However, unlike gas molecules, their movement is very fast and random. Some move left, some right, some upward. despite this random motion, their net movement in a specific direction is zero. When a potential difference is applied, it causes the electrons to move in a specific direction. This average velocity with which electrons drift under the influence of an electric field is called drift speed. On the other hand, current density is defined as the ratio of electric current to the cross-sectional area through which the current flows. Now consider an exam question related to this topic. This paper is of May-June 2023, Paper 2, question number 6, Part B. A cylindrical wire has length L and resistance R. The total number of free electrons contained in the volume of the wire is N. Each free electron has charge E. The potential difference between the ends of the wire is V. Determine expressions in terms of some or all of the symbols E, L, N, R and V for Part 1, the current in the wire. So we have to express the current in terms of E, L, N, R and V. Recall Ohm's law, current would be V by R. In the next part we have to find drift speed. To find the drift speed, consider the formula, which we have recently derived, I is equal to NAVQ. Rearrange it for drift speed. Now, substitute V by R in place of I and E in place of Q, and by definition of charge density, which is number of electrons per unit volume, substitute N equals to capital N over AL, where A and L combine to form volume. After substituting, rearrange to get the desired expression for the drift speed. In the next part, we have to find the average time taken for a free electron to move along the full length of the wire. For this, consider the formula of drift speed, which we have derived in the previous part. Substitute L by T in place of V, and now solve for T. So this is the solution of this question. And this is another question related to this topic. We will solve it in the last part of the video. And this is another question related to this topic. We will solve it in the last part of the video. The next topic is conventional current. The current that flows from positive terminal of battery to negative terminal of battery is termed conventional current. However, in the case of metals, the actual flow of current is due to electrons. Electrons carry a negative charge, so they move from the negative terminal of the battery towards the positive terminal, as opposite charges attract. This leads to a question: why do we define current in the opposite direction of electron flow? The answer lies in historical convention. When electricity was first discovered, the direction of current was defined based on the flow of positive charge from higher potential to lower potential. Just like water flows from a high level to a low level, or heat flows from a hot object to a colder one, it was assumed that electric current also flows from high potential to low potential. Later, when electrons were discovered, it became clear that they actually flow from the negative terminal, low potential, to the positive terminal, high potential, which is opposite to the assumed direction. But instead of redefining everything, scientists introduced the concept of conventional current, a flow that behaves as if positive charges were moving from positive to negative. This convention is still followed today because it simplifies analysis and calculations. Actually, the flow of positive charge has the same effect as the flow of electrons. To understand this better, imagine two boys riding bicycles down a road. One says, "The trees are moving behind us," while the other replies, "No, we are moving forward, the trees are stationary." Technically, the trees aren't moving, it's the boys. But from their perspective, it feels like the trees are moving. Similarly, even though electrons are the actual moving particles, we talk about current as if positive charges are moving in the opposite direction. So now, we have two terms, electronic current and conventional current. Throughout this course, we will use conventional current. So whenever we mention the direction of current, it is always taken from the positive terminal to the negative terminal. Our next topic is potential difference and power. But first, let's understand the concept of electric potential. To make this easier, I'll begin with an example you might already be familiar with: gravitational potential energy. Imagine an object lying on the ground. At this point, its gravitational potential energy is zero because its height is zero. Now, if we lift this object upwards, it gains potential energy. But where does this energy come from? It comes from the work we do while lifting the object. This gained energy is stored due to the gravitational field of the Earth. If there were no gravitational field, there would be no potential energy. So remember this important point: wherever there is a field, there is a possibility of work being done. Now let's relate this to electricity. Just like the gravitational field, an electric field can also do work. Suppose we place a positive charge in a uniform electric field. The electric field exerts a force on the charge, just like gravity acts on a mass. If we try to move this positive charge toward the positive terminal, we have to apply a force, because we are moving it against the direction of the field, similar to lifting a mass upward against gravity. So, based on this concept, electric potential is defined as the amount of work done in moving a unit positive charge from one point to another within an electric field. More specifically, we also call this concept potential difference. It is defined as the energy per unit charge when a charge moves from one point, say, point A, to another point, point B, in an electric field. This is very similar to gravitational potential difference, which is the amount of work required to lift a mass from one height to another. For example, if the gravitational potential energy at point A is 10 joules and at point B it is 20 joules, then the difference, 10 joules divided by mass, represents the gravitational potential difference. In the same way, if a charge has 10 joules of electric potential energy at point A and 20 joules at point B, the difference, 10 joules, divided by the charge gives us the electric potential difference between A and B. There is also another important term, absolute electric potential. This is defined as the electric potential at a point when the reference point is taken at infinity, where the potential is considered to be zero. In this case, the potential difference between infinity and a given point becomes the absolute electric potential at that point. The unit of potential difference is the volt, which is defined as the potential difference between 2 points in a circuit when 1 joule of energy is required to move 1 coulomb of charge between them. Potential difference is measured using a device called a voltmeter. That's why we often refer to potential difference simply as voltage. To measure voltage, the voltmeter is always connected in parallel with the component across which we want to measure the voltage. Take a look at this diagram. We are measuring the voltage across a variable resistor. The voltmeter is showing a reading of 5 volts. Now here's a question for you. Can you figure out the value of the variable resistor that gives a voltage of 5 volts? Take a moment, pause the video and think about it. Let's solve it together. It's actually very simple. Inside the battery, there is an internal resistance of 50 ohms and the EMF, electromotive force, of the battery is 10 volts. Now this 10 volts gets divided between the internal resistance and the variable resistor. We see that the voltmeter shows 5 volts across the variable resistor, and the remaining 5 volts must be across the internal resistance. So, according to the voltage divider rule, both resistors are dropping the same voltage, 5V each. This means the variable resistor must have the same resistance as the internal one, which is 50 ohms. If this seems a bit confusing, don't worry. We will learn in the next lecture, which is on DC circuits. Next, let's talk about resistance. Resistance is a measure of how much a material opposes the flow of electric current. In simple terms, it tells us how hard it is for electrons to move through a conductor. If we compare it to mechanics, resistance is like friction. Friction opposes the motion of an object and converts some useful energy into heat. Similarly, when current flows through a resistor, the resistance opposes the movement of electrons, and some electrical energy is converted into heat. This heating effect is actually useful in appliances like electric heaters, irons, and geysers, where heat is the desired output. The unit of resistance is the ohm, represented by the symbol omega. When a potential difference of 1 volt causes a current of 1 ampere to flow through a conductor. Resistance also depends on temperature, especially in metals. As the temperature of a metallic conductor increases, the atoms vibrate more intensely, leading to more collisions between free electrons and atoms. As a result, resistance increases with temperature. However, in materials like semiconductors and thermistors, the behavior is different. As temperature increases, more charge carriers become available, so the resistance decreases. Our next topic is Ohm's law, which states that the current flowing through a conductor is directly proportional to the potential difference, or voltage, across it, provided that the physical conditions, such as the temperature of the conductor, remain constant. This means that if we increase the voltage, the current increases in the same proportion, as long as the conductor's properties do not change. The graphical representation of Ohm's law is an IV graph, where current is plotted against voltage. This graph is a straight line that passes through the origin, showing a linear relationship. The slope of this line is equal to 1 divided by the resistance, or 1 over R. This linear behavior indicates that the resistance remains constant when the physical conditions are unchanged. Here are the IV characteristics of some materials, including the diode, filament of a bulb, and thermistor. All of them exhibit nomic behavior, meaning their IV graphs are not straight lines. In a diode, initially, the current does not increase significantly with voltage. However, once the voltage reaches a certain threshold, around 0.6 volts for a silicon diode, the current increases rapidly, showing a sharp upward curve. For a filament bulb, as the current increases, the filament heats up, which increases its resistance. As a result, the IV curve bends, showing that current no longer increases linearly with voltage. In the case of a thermistor, especially a negative temperature coefficient or NTC thermistor, the resistance decreases with increasing temperature. So, as voltage increases and it heats up, the current increases more rapidly, resulting in a curve that gets steeper with voltage. Since the resistance of a thermistor depends on temperature, it is commonly used as a temperature sensor. A thermistor is a type of resistor whose resistance changes significantly with temperature. The word thermistor is derived from the words thermal and resistor. Now, why does a thermistor not obey Ohm's law? This is because thermistors are made from semiconductor materials such as metal oxides, including manganese, nickel, or cobalt oxides. As the temperature rises, thermal energy breaks more covalent bonds in the semiconductor lattice, releasing additional free electrons and holes. This increases the number of charge carriers, allowing more current to flow at the same voltage. As a result, the resistance decreases as the temperature increases, leading to nonlinear, nomic behavior. Next, we are going to discuss how resistance is also affected by the physical dimensions of a conductor. One important factor is the length of the wire. Increasing the length increases resistance, much like how a longer pipe makes it harder for water to flow through. Another factor is the cross-sectional area of the wire. Increasing the area decreases resistance, just like a wider pipe allows more water to flow through easily. This relationship between resistance, length, and area is mathematically expressed as R is equal to ρ times LA, where R is resistance, ρ is the resistivity of the material, L is the length of the conductor, and A is the cross-sectional area. Resistivity is also called specific resistance of a material. It is defined as the electrical resistance measured across opposite faces of a cube of material that is 1 meter in length. Here's a conceptual exam question: if we double the length of a wire, what happens to its resistivity? The answer is that resistivity remains unchanged because it is a property of the material itself. Changing the length or dimensions of the wire does not affect resistivity. It depends only on the type of material used. There is another related term called conductivity, which is defined as the reciprocal of resistivity. It indicates how easily a material allows electric current to flow. A material with high conductivity has low resistivity and vice versa. This table shows the resistivity values of various materials. As you can see, metals like silver and copper have extremely low resistivity, making them excellent conductors. In contrast, Materials like rubber, glass, and PVC have very high resistivity, making them effective insulators. Now let's talk about something truly fascinating: superconductors. Superconductors are materials that have zero electrical resistance when cooled below a certain temperature called the critical temperature or TC. This means current can flow through them without any energy loss. You can think of a superconductor like a frictionless road for electricity. Once the current starts flowing, it keeps going without slowing down. Because of this, superconductors are used in MRI machines, maglev trains, and are being explored for use in quantum computing and efficient power systems. Most superconductors require extremely low temperatures to function, which limits their everyday use. However, scientists are working to discover materials that work at higher temperatures to make this technology more practical. Our next topic is the light-dependent resistor, or LDR for short. An LDR is a special type of resistor whose resistance varies with the light intensity falling on it. In darkness, its resistance is very high, so very little current flows through it. But as the light intensity increases, its resistance decreases, allowing more current to flow. This behavior is explained by the photoelectric effect. Light energy excites electrons in the material, making them available for conduction. The brighter the light, the more free electrons are available, and the lower the resistance becomes. Because of this unique property, LDRs are widely used in automatic streetlights, light-activated alarms, and other circuits that need to respond to changing light levels. Here is the circuit diagram for an automatic street lighting circuit, where the LDR is used to switch the lights on at night and off during the day automatically. Now let's talk about electric power. Electric power is the rate at which electrical energy is transferred or converted in a circuit. In simple terms, it tells us how quickly energy is being used or supplied. Mathematically, power can be calculated using the formula P is equal to V times I, where P is power, V is the potential difference in volts, and I is the current in amperes. This means that if we increase the voltage or current in a circuit, the power delivered will also increase. Using Ohm's law, we can also express power in two other forms. Now that we've completed the theory, let's move on to solving some past paper questions. The question we are going to solve is from the November 2023 exam, Paper 2, Question 6. In this question, the resistance per unit length of a wire is given, which is 0.92 ohms per meter, and we are also given the cross-sectional area of the wire. To solve this, we'll use the formula for specific resistance. Rearrange the formula. Now, substitute the given values into the formula. And calculate the answer, which is 4.9 into 10 raised power minus 7 ohm meter. Now this is the B part of the question. In the circuit diagram, we are given a battery with negligible internal resistance connected in series with a fixed resistor and a light-dependent resistor, or LDR. A voltmeter is connected in parallel across the LDR, and it shows a reading of 6.4 volts. We are asked to show that the current passing through the LDR is 4 milliamperes. This is a very simple question. The mention of the fixed resistor is just there to distract or confuse you. You actually don't need to use it for this part. You can solve this directly using Ohm's law. Here, the voltage across the LDR is 6.4 volts and the resistance of the LDR is 1600 ohms. Substituting these values into the formula and solve to get the result. This is the B part of the question. We have already solved this question when we discussed the topic of specific resistance, and here is the complete solution. The next question we are going to solve is from the May-June 2021 exam, Paper 2, Question 5. In Part A, we have to define the unit of resistance, which is ohm, and here is the definition.
Next is the B part. Here is the statement of the question. A wire is made of metal of resistivity ρ. The length L of the wire is gradually increased. Assume that the volume 5 of the wire remains constant as its length is increased. Show that the resistance R of the extending wire is proportional to L square. Consider the formula of specific resistance, substitute V over L in place of A. And now according to the statement of question, volume remains constant and ρ is also a constant, so it has been proved that the resistance R of the extending wire is proportional to L square. The next question we're going to solve is from the May-June 2020 exam, Paper 2, Question 5. Part A. Metal wire is used to connect a power supply to a lamp. The wire has a total resistance of 3.4 ohms and the metal has a resistivity of 2.6 into 10 raised power minus 8 ohm meter. The total length of the wire is 59 meters. Show that the wire has a cross-sectional area of 4.5 into 10 raised power minus 7 meter square. Let's solve this question. So three things are given, which is ρ, resistance and length, so use formula of resistivity, substitute the values in the formula, and got the result. Part 2. The potential difference across the total length of wire is 1.8 V. Calculate the current in the wire. Voltage is given, which is 1.8 volts. Take the resistance from part A, which is 3.4 ohms. Now use the Ohm's law and substitute the values to get the result. Part 3. The number density of the free electrons in the wire is 6.1 into 10 raised power 28 per meter cube. Calculate the average drift speed of the free electrons in the wire. Use the formula, I is equal to NAVQ. Substitute the values. After calculation, result is 1.2 into 10 raised power minus 4 meter per second. This is the B part of the question. A different wire carries a current. This wire has a part that is thinner than the rest of the wire, as shown in figure 5.1. Part A. State and explain qualitatively how the average drift speed of the free electrons in the thinner part compares with that in the rest of the wire. To solve this, recall the formula of current. I is equal to NAVQ, as area in thinner part is small, so according to the formula, other quantities such as N, V and Q are constant, so average drift speed in thinner part is greater. Part 2. State and explain whether the power dissipated in the thinner part is the same, less or more than the power dissipated in an equal length of the rest of the wire. The thinner part of the wire has a higher resistance because its cross-sectional area is smaller. As current flows through it, the electrons experience greater opposition to their motion. Since electrical power dissipation is given by P is I square R, the higher resistance causes more power to be dissipated in the thinner section compared to an equal length of the rest of the wire. Part C. Three resistors have resistances of 180 ohms, 90 ohms and 30 ohms. Part A. Sketch a diagram showing how two of these three resistors may be connected together to give a combined resistance of 60 ohms between the terminals shown. Ensure you label the values of the resistances in your diagram. Recall the series and parallel combination of resistors. In case of series combination, if we add the values, then it will exceed from 60, so only parallel combination is possible. And if we use 180 ohm and 90 ohm in parallel, then its equivalent resistance would be 60 ohm. The next question we're going to solve is from the November 2017 exam, Paper 2, Question 5. Part A. State what is meant by an electric current. Electric current is the flow of charge carriers. Part B is a similar question, we have already solved. In theory, move to the next part. A metal wire in a circuit is damaged. The resistivity of the metal is unchanged, but the cross-sectional area of the wire is reduced over a length of 3.0 mm, as shown in Fig. 6.2. The wire has diameter D at cross-section X and diameter 0.69 D at cross-section Y. The current in the wire is 0.50 A. Determine the ratio. Consider the formula for current for each part X and Y. Cancel the similar terms. Rearrange formula. Substitute the formula of area to have the relationship in terms of diameter. Substitute the values in the formula. Calculate using calculator. The result is 2.1. Thanks for watching. Don't forget to like and subscribe.